Welcome to the demo on how to use Scientific SPARQL from inside MATLAB. The first thing to do is to start the Scientific SPARQL Database Manager server. In our case, it is deployed on a remote Linux machine, and here I'm using the terminal to run the start script. Now we are running MATLAB interpreter on the client. We import the SciSPARQL library. Here we give mat option to initialize the client so that it knows it can send .mat files to the server. We obtain the connection to the server. It is that simple. Now we're going to use a certain RDF namespace for our experiment. So SciSPARQL allows us to set a session-wide prefix. Here an empty prefix for our bstab namespace. For simplicity, we are about to start building our RDF graph from the scratch, so we clear whatever might be there in the default graph. Now we use standard SPARQL update syntax to insert some metadata about our scientific experiment. We will identify it as experiment 1 node and store a bunch of parameters that are constant. Another way to insert a triple where we can directly supply MATLAB values is calling insert method of our connection object. Here we supply two URIs and one-dimensional MATLAB array. This triple will also become part of our RDF graph on the server. Now we're going to add a lot more data. As most MATLAB users do, we have it in variables in a set of files. Our input.mat contains parameter cases and an annotated array. Since we are now utilizing semantic web, we are going to annotate these values so that semantics will become more clear to the future users. And here our script is to do this. For each parameter case, we create a task node with a number. Since we are building the graph, first we record that the new task node belongs to our experiment 1. And now the rows in our parameters array finally get meaningful names like K1 or KD, so our metadata becomes well annotated. As a last step for each parameter case, we get the massive numeric data that comes as a result of computer simulation. We could have run the simulation right here, but we happened to run it before and stored the outcomes in a set of .mat files on the client machine, where the parameter case and realization number are encoded into the file name, a very common practice in the absence of databases. Now we incorporate our massive arrays into the RDF graph by shipping them to the server and connecting them as U properties of our task nodes. This is all data integration effort we need. So we have created our RDF graph. And for a toy graph like this, we can see it all with the most basic SPARQL query. We can even export it to an triples file if we like. And of course we can save the server image, so we can restart the server with the current data snapshot. Now let's try some simple Scientific SPARQL query, like selecting row number 15 from U matrix associated with task 1. Now we get back the scan object that provides access to query results. It contains rows and columns, and the first row is the current one. The only value is our one-dimensional array, a projection of the matrix that we received from the server. Scientific SPARQL allows to define functions that can later be called directly or from queries and updates. These can be foreign functions in Java, Python or C, on native SciSPARQL functions defined as parameterized queries. In that case, the concept is similar to SQL stored functions, but a bit more powerful. The purpose of this particular function is to sum up certain rows in a matrix, thus building a row of column-wise totals. The rows are selected based on a modulus rule. That's why we need the other two parameters, the number of species modeled and the species of interest. Notice that I variable, it is not a parameter and not bound by a graph pattern or expression, but since it is used as a subscript to a matrix, it automatically assumes all possible values that the first subscript to that particular matrix might have. The filter denotes the set of bindings for I, and the row numbers are only those that we are interested in. The sum function here is an aggregate function. It takes a set of values, 1D arrays in our case, and returns single value, the rows of totals. So it is the way to specify a conditional sum in SciSPARQL. The example and queries in this demo are taken from our eScience publication last year. They are quite realistic. This first one looks like a normal SPARQL query with graph patterns here. One interesting part is the unbound variable j that runs through all available common subscripts of our t-span vector and the result of total species function. This way we return two vectors as a sequence of pairs of their respective elements. As usual, we obtain a scan object where each row will have two numbers. Now, since we want to plot the result as a time series, we collect the results back into a two-column MATLAB array. The simple cycle here is a bit more general. It could actually handle any number of columns. Now we can see our time series and plot it. That's what MATLAB is really good at. The second query is selecting the data from our RDF graph based on ranges of parameters. It is interested in one time point, that is 1.5 seconds from the beginning of simulation. The variable t is bound by the filter to point to the specific element in a t-span vector, and thus to the specific column in U matrices. So, first we select task nodes that belong to experiment 1 and have the parameters in certain ranges. Then, for each such task, we project the U matrix to specific rows. We provide origin and stride here, and the specific columns. What we get is a much smaller array that we apply array sum function upon to simply sum up its elements. The query will return a single number for each parameter case discovered. For the third query, we define another function to compute a numeric property of a task node based on its stored properties. This function has some graph patterns to receive the relevant data and some rather straightforward post-processing here. Now we want to find a task node representing the parameter case where this function is at its maximum. Yes, Scientific SPARQL has second-order functions like argmax. In this simple case, where we just define a function of one argument returning a number, we just call argmax directly on the function's name. SciSPARQL takes care of the domain for its arguments. In our case, it is limited to be the task nodes connected to experiments, where task and experiments have other properties used in the graph patterns inside the function. The result is a graph node, which we can query for its further properties, for example, the parameter case. This is the end of our short demo. Feel free to learn more about Scientific SPARQL at our project homepage.